Hi, my name is Bryan McCloskey, postdoctoral researcher here at IBM Research Center in San Jose, California. I'd like to talk to you today about an article that we recently published in Journal of Physical Chemistry Letters on the promise and challenges of lithium-air batteries. We've been working on this project for about a year and a half now at IBM, and the motivation behind this is the U.S.'s enormous dependence on oil, especially for transportation. Certainly if we want to get away from using oil in the transportation sector, we want to use alternative energy sources, and we need a method to store any energy that we get from those alternative energy sources. And that makes the improving battery technology critically important, especially the energy densities in those batteries. And therefore, lithium-air, we're exploring lithium-air batteries as a potential alternative for current state-of-the-art battery technologies.
I'm Girish Gopalakrishnan. I'm an electrochemist at IBM Research Center working on the Lithium-Air battery project. What I'm going to explain today is the working principle of a rechargeable lithium-ion battery, which is commercially used today in our cell phones, laptops, etc. What you have in a lithium-ion battery is a layered transition metal oxide cathode, and you have a graphitic anode. And most of the lithium ions are stored inside the galleries of the cathode material. And during the charging of a battery, that is typically the process that happens first in a lithium-ion battery, you have lithium ions deintercalating from the anode and intercalating into the anode, and electrons travel through the external circuit. During the discharge of this lithium-ion battery, you have lithium ions deintercalating and getting integrated into the cathode. Advantages of using lithium-air battery, you can see that lithium is possibly a light element, and comparing that with an air cathode makes this really light, and hence the advantages of its high energy density, and also the electrochemical equivalence of metallic lithium is very high. In a lithium-air battery, what you have is a metallic lithium as the anode. You have a porous carbon cathode and an electrolyte which is ionically conducting. During the discharge of a battery, you have lithium ions coming out into solution, and in the presence of oxygen from the external source, like for example air, and in the presence of electron, you form lithium peroxide or oxide depending upon how much you discharge the battery. Why rechargeable lithium-ion batteries are important? If you look at the energy density, that is the amount of energy that can be extracted out of a kilogram of material. Your lead-acid batteries have an energy density of around 40 watt-hour per kilogram, and lithium-ion has substantially higher, around 120 watt-hours per kilogram. But if you look at lithium-air, this has substantially higher compared to that of any other battery system. For example, in this case, this figure clearly shows that at around 1700 watt-hours per kilogram.
This is a typical lab that we evaluate the fundamental properties of lithium-air batteries in terms of the different cathode structures and modification with electrolyte, etc. What I'm going to show here is actually how we build a cell, and we commonly use what is called a swage lock cell arrangement. What we have here is a typical swage lock cell, and we put the porous carbon cathode here, and you have a separator which is a glassy material, or it could be a common cell guard separator, and then we put lithium metal on top of that, and a typical cell design after that arrangement would look something like this shown here. It's important that this cell is assembled inside the glove box because of the reactivity issues associated with metallic lithium. So what you see here is oxygen being fed here, and you have your cathode, electrolyte and metallic lithium, where the reaction happens.
One of the most important aspects of any rechargeable battery is the formation of the desired electrochemical products at the cathode during discharge, and then the efficient decomposition of those products upon recharge. For example, in a lithium-air cell, we'd like lithium ions to combine with oxygen molecules via two-electron process to form lithium peroxide, and then have that lithium peroxide decompose once again into lithium ions and oxygen molecules upon recharge. Therefore, it's very important for us to be able to sample the gases that are evolved in our electrochemical cells. To do this, we use this system here, a differential electrochemical mass spectrometer. Here we can send the gases from our cells to this mass spectrometer that you see here. We can quantify the amount of gases that are involved, and we can also see exactly what type of gases are involved as well. This gives us a much better understanding of the chemical processes that are occurring within our electrochemical cells.